Oh my god. Oh my god. Okay. I did not realize I had not clicked on the start stream button. Good lord. Okay, so I'm gonna start again. I'm so sorry, guys. Right, okay, so welcome to the third this third live stream. Oh my god. I had no idea the stream did not start. I am so sorry, guys. Yeah, so this is a new setup. Totally sorry about that. That's ridiculous. At least I've done a sort of an early run. So, yeah, at this point, we've had a few updates. The first update is that we are actually in a new location. This, as you can see, is a red and black tiled background. I have a couple of EA game portraits up here because I happen to like the art. And you may notice that the audio is a little bit reverby. My apologies. This is not 100%. I do need more hardware in here, but this is just a temporary location. So I'm actually in a new place. I have a nice 3-bedroom house, and then I also have a 25 by 25 shop that I am working on to finish out, at least for insulation at the moment. Thanks. And for now, I'm actually streaming from my bedroom, but I've got this nice setup so you guys don't have to see all the mess. But yes, it is actually in progress. I have a bunch of buildings that are going to be put out on the property, and once this is all sorted, this will be a really, really nice setup. We'll be able to move the camera around. I'll be able to talk to you guys about stuff in a more coherent fashion and stuff like that. Right, so... Yeah, that really did happen. Sincere apologies for that. But yeah, so let's see. Other updates. The V128 project. We haven't done a whole lot on the electronics yet. Since I've been moving, this has been kind of difficult to get much work done for it. So in the moment, I actually haven't made a lot of progress on the software. And let's see. Also, the hardware, the mechanicals, specifically the enclosure that we're working on, that Matthew is working on awesomely, we found a model, like an actual accurate model of the original Commodore 128D, the one with the carrying handle, and the one that Bill Hurd still has. And Matthew's working on it right now. But yes, the idea here is that since just about nobody had a 128D and they're incredibly rare, we might as well just use that as our enclosure. It's a cooler design. It's actually really, really neat stuff. So Matthew has done an amazing job tracking down the owner of this particular model, and he's working on trying to integrate a lot of our hardware into that thing. So we'll see about how that goes. Because obviously we're building a scaled down unit. We're not going to be able to put the keyboard actually underneath it, but we'll see where it goes. And I believe Olapar is also in the progress of testing out a couple of USB circuits. So I'm not sure what the status on that is right now because I've been disconnected for the last couple of weeks. But yeah, in terms of the V128 project, things are moving. They're a little bit slow at the moment, so please bear with us. But if you want to join with us, you can join us on the Discord. I'll have a link later. And then also, we're in the V128 channel, so definitely take a look. There's all kinds of stuff that can be done to work on. Let's see. Other announcements? I don't think there are any, so let's get to the stuff. Let's switch over to Emacs. And since I started the stream late, my apologies. I actually already explained this, but I'm going to do it again so that we can get back onto this. So somebody asked in the last stream, do we need to save the registers in the interrupt callback? And if you recall, our actual interrupt callback, so interrupt handler, and my apologies for the sound of the keyboard. I cannot get noise torch to actually work anymore, so I need to go and update that. Oh, excellent! It was you, Mark. Okay, good. So then I'm glad you're here, so you can see this. So our interrupt callback here, you'll see we don't actually save the registers. Now, I know a priori, we actually don't need to do this. We don't need to save these registers, and in fact, we shouldn't. But you'll also notice that we don't restore them here either. We're actually calling into the system's ISR. Now, there's a reason for this. If we take a look at the mapping the Commodore 128 documentation, let me switch back to where I was. This may take me a little bit. It's I believe it's the power behind Commodore 128 graphics. It's up like in here. Yeah, here it is. Yeah, so on page 251 of the Commodore 128 Programmer's Reference Guide, there is an interesting program listed here that does a raster interrupt split. So effectively, it's going to drive the VIC-2 into two different video modes based on a specific raster line on the screen. And what they do in their interrupt handler, and it's a little hard to see, they actually, where is it? Initialize interrupt. So this assembler that they're using in this particular listing is really, really old. It's one of Commodore's assemblers, and it's a little funky because any word in the 0th column prefixing a space is a label. And they sort of like do this weird nomenclature where they have this short word, a space, and then an opcode. And then anything that's after that first space is considered to be an opcode, or an instruction. Let me put it that way. So finding labels in this is a little painful, but essentially when they set up their interrupt, what they do is they read the interrupt location from the interrupt vector for the raster interrupt. They store that in temp, and then they replace it with their ISR called mine. And then if we go down to mine, or their ISR, first thing they do is they load from a register, and then they store to a register. And this is just to acknowledge the interrupt. So just like we do in our source code up here, where we do this LDA VIC interrupt, they're doing the same thing over in their source code here. But they're not doing anything to save the registers either. And there's a reason for that. When we replace this interrupt handler, we're not actually replacing the whole interrupt handler. We're actually wedging, this is actually called wedging, we're wedging our interrupt handler ahead of the system interrupt handler. So going back to our source code, this is why we call sysISR pointer. So let's take a look at how interrupts actually work on a 6510, because this is kind of important, because otherwise, like, you don't really quite understand how this works on a 128 or even on a Commodore 64, because it works exactly the same there. So to do that, we're actually going to take a look at the Commodore 6510 data sheet. And if you're, sorry, go ahead. Does not sysISR pointer not save the regs, and by that point you've stomped on them. So I'm getting to that. Hang on. Stay with me. So if you take a look at the pin configuration for the 6510, you can think of this as sort of like a schematic look of the actual chip. And there's only one IRQ line going into this chip. We have a whole bunch of address lines. We've got our ground, we've got our power, we've got AEC, which is a different thing. We have Phi1, that's our clock. Phi2, that's our other clock. It's the other half of the phase. We have read-write for memory access. We've got our data bits. And then we have these P bits and then more address pins. But we only have the single ISR. Sorry, IRQ. So if you think about the hardware design of the Commodore 128, we have the CIAs. These things have timers in them. They can interrupt the chip. We have the VIC. It can interrupt the chip. And we have a bunch of other peripherals that can all interrupt the chip. So since this is a digital line, we only get a 1 or a 0 on this. So that means that our IRQ handler, the 6510's IRQ handler, whatever's written in ROM, has to identify where those IRQs are coming from. And when we replace our interrupt handler, we're not replacing the one in ROM, we're just replacing part of it. So if we go down a little bit further to the description of how this works, the 6510, being a non-RISC system, does some things for us, but not everything. The first thing it does during an interrupt request is that the program counter and the processor status register are both stored onto the stack. That's done automatically for us. Yes, precisely, Mark. We are just replacing the interrupt vector for the raster interrupt. So I'm actually going to get into the disassembly of this so you can see it a little better. But effectively, the CPU is already just pushing stuff onto the stack for us. It does not push A, X, Y, or S. And that's important. But the datasheet tells us that it actually loads the interrupt, it loads the program counter for the interrupt from address FFFE. So let's get Vice up. And let's take a look at this. Oh, whoa, what's going on here? Oh, that's the wrong Vice. Technical difficulties, apologies. X128, there we go. Yeah, I didn't save the settings. Apologies. Let me fix this. This again is because I had already explained this to you guys. You just couldn't hear me. Okay, so first thing I'm going to do is I'm going to fix the joysticks because right now my arrow keys are not set up right. Hey, Erebos, welcome, welcome. Okay, that should probably do it. And then I'm going to disable the joysticks. There we go. Okay. And then video, because this is driving me crazy. Okay. Right. So let's take a look at that location. So we know offhand from the data sheet that the 6510 is going to figure out where to jump into RAM based upon the address that's stored at FFFE. So if we do a memory dump of FFFE, and it's going to wrap around because we're at the end of all of the RAM, right? You'll see right here, we have this address, 17FF. Now this isn't actually 17FF because the 6510 loads the low address from FFFE and then the high address from FFFF because it's doing it in Little Endian order. So this is address FF17. So let's go ahead and disassemble that. Let's see what that is. So we do this in bank F because we want access to all the ROM. And then we say FF17. Right? And here we go. There's our answer right there. Right for you, Mark. The very beginning of this interrupt handler is they push A, they transfer X, then they push A, then they transfer Y, and they push A. Yeah. Now, there is a problem with this. There's a register they left out. That's the stack pointer. Because every time this happens, yeah, they also push the MMU status as well. So that's what this next thing here is. They're doing LDA FF00, and then they push that push that from A into the stack as well. And that is so that they can maintain the same MMU status when they jump back, because the MMU is not part of the CPU. If they don't do that, the interrupt routine can then kind of like, basically the main program will get screwed up because the MMU won't be in the same mapping. And that could result in writing into other locations of RAM that they don't want to. So they have to store that. But if we look at the registers here, right, we have this extra register. We've got the stack pointer up at the top right here. That's SP. And you'll see right now it's set to F9. Now in the 6510, the stack does not move. It's always at page 1. So this is a bit important because if we take a look at $, I believe it's, I think we can do 0, 0, 1, and then 0, 0. Right, that's all the stuff that's in our stack. And we only have 256 bytes of this. and the stack pointer is actually starting from the bottom and going up. So there's something to know about this. When the interrupt service routine fires, we're using up a bunch of bytes in the stack. So if that stack pointer is all the way down to, like, say 0, for instance, it's going to wrap around, and it's actually going to start overwriting the stuff at the beginning of the stack. So as user program developers that we are, we have to be mindful how many subroutines that we jump into in our main program. If we jump into too many, we'll end up with a stack overflow, and it will clobber our stack and screw up things later. So in the 128's case, we have the MMU, and the MMU allows us to be able to, yes, everything for the 6510 applies to the 8502. I can't find a datasheet for the 8502. However, the only thing you need to remember about the 8502 is that basically the only thing that's different is the layout of these pins. The 8510 does something different with these pins that are labeled P. And I believe also, well, no, the DB pins, these are the data pins. Those are always there. The address pins are always there. They don't do any multiplexing on the 6510 like they do on the 65816. But the P pins change, and the overall number of pins that they have in the package change. So in the 8502, they changed this layout. They still only have one interrupt pin. They still only have one NMI pin. And they still have all the rest of that stuff. But effectively, the ISA is exactly the same. All the interrupts, all the behavior of the chip, all of that stuff is basically the same. So, yeah, that's the answer to that question. So, yeah, in effect, in our interrupt routine, we don't have to save anything, and we don't have to restore anything, because we jump into the system IRQ handler, which will take care of that for us, because this actually includes an RTI later on in the ROM. So now I can go over to our to-do and mark that as done. So, wahaha. Okay, so let's get back into the actual game here. So the last time we were talking, we were discussing the raster interrupt routine, and then we got into joystick input, or at least we started to, and I had to end the stream because we were running out of time. Yeah, so joystick input. Now I covered this in another video before, and actually I'm going to quit Vice so that we can deal with this a little better. Yeah, so in one of my videos, I started talking about joysticks, and this was the CIA video where I had my friend Greg show up as like the CIA guy. And it was kind of corny and probably a little bit difficult to really like get the meat of the problem sorted. But effectively, in our game, we're going to use a shadow register of our own design to store the joystick state. And not to store the joystick state, to store our sprite's position. And we know that we want to have the fire buttons fire off a bullet so that we can actually effectively do something with the player, basically have a game, right? We want a maximum of 3 bullets available per player. Now, the reason I chose 3 is because the VIC-2 has, let's see, we've got player 1, we got player 2, and then we have 3 bullets, and we have 3 more bullets, so we're up to 8. There is, I believe, so we only have 8 sprites, right? So we get 3 bullets for each player, and that means they can have 3 bullets out on the screen at one time, so we can have a maximum of 6 bullets on the screen at once. Right, and then we have in our shadow registers, or our player or tracking information registers, memory locations, these are not registers, they are storing a direction bit. So if we go back to our source code, you'll see that the init sprite routine has this facing value. Init sprite macro has a facing value that we use. And that tells us which direction that the tank is facing, right? So we're kind of abusing this bit. We are also using this to determine whether or not a bullet is alive or dead. And we can do that because, going back to our source code again, we have our direction flags, but you'll see they're all at least 1. So we've got 1, 2, 4, and 8. If it's 0, then we know that that particular sprite is not being used or it's dead. So effectively, when we deal with these direction bits, right, we have bullets that are going to be on screen for a finite amount of time, and then they're either going to hit the player or they're going to get to the edge of the playfield. At that point, we don't care about them anymore. We don't need to update them. We don't need to mess with them. They're not active anymore. If there's a collision with the sprite and the player, it should not cause one of the players to die. So we use the direction flag to determine whether or not a bullet is alive or not by setting it to 0. And then also we have a 30 frame delay between spawns. And this is so that there's a bit more impact. This is kind of like a game design decision, right? Because if a player dies, we want that to be kind of a momentous event. We don't want this to be like okay, the player just suddenly dies and all the tanks get reset and what happened? I don't know. I can't track it, right? So we put a 30 frame delay between spawns using a countdown counter. Sorry, this is actually not for that. This is actually for the bullets. My apologies. So we use the 30 frame delay to make sure that you can't fire all 3 bullets all at once, because the 8510, 8502 is reading from the joystick port faster than a human can possibly react. So if the time at which you press the button and the time at which you release it is long enough to where the 8502 could actually end up spawning all 3 bullets at the same time, and then you can't fire anymore. So we put a 30 frame delay in there so that you have time to be able to deal with that release. Right, so going back to the source code. Our interrupt routine, like most of this code, is actually still very similar. Right, we have our standard interrupt setup. Yes, it also handles any debounce. So for those of you who are not familiar with how switches work, remember, you're dealing with 2 pieces of metal. At some point, those 2 pieces of metal are going to collide to close the switch. When that happens, you can't see it, but what's happening is those pieces of metal are bouncing against each other. And when that happens, they're doing like this. So they're making and breaking the circuit over and over and over again. And so from a switch perspective, it is actually possible, because our CPU is moving 1,000 times a second, it is possible to read both 0s and 1s while we are bouncing. So you have to de-bounce the switch. And in this case, because we're reading from the CIAs, they don't do any debouncing for us. They just read from these things as though they're GPIOs. So we in the software have to deal with that. And the way we can do that is we can put this 30 frame delay between spawns, between reads of the joystick button. So when we get into our main game loop, remember that we're using this frame start flag. This allows us to know when we should actually start processing things like movement of players, updating the sprites, and that kind of stuff. So at the beginning of each frame, we call this routine called handle input. Now, X is a parameter register that we're using to determine which joystick. I know, but the thing is, actually, Vincent, so you're saying those days, but this is still true today. So when you're dealing with inputs on, say, a Raspberry Pi, the Raspberry Pi's GPIOs are also not debounced. So you have to deal with that. Same thing is true on, say, like an Arduino. All of the GPIOs are raw. So when you write your Arduino code, you still have to go in there and you still have to have a routine to debounce all those switches. And there's a whole bunch of algorithms that are specific for this, and there's a million different ways of doing it. There's also ways of solving this in hardware, but in general, solving it in hardware is expensive. So most of the time, we just do it in software. And that's actually one of the other reasons why I'm doing this channel, is because when you're looking at these embedded systems, it's easy to get lost in the weeds because there's all these random crazy things happening on the systems, but all the principles are exactly the same today, even on modern hardware. So the old hardware is actually still totally valid in today's context. So everything that we do in this channel is 100% applicable. You still have to read data sheets. You still have to understand basics of electronics. And so that's why it's good to learn, good to play with this stuff. So in any case, going back to the joystick stuff, handle input is our routine, a single routine that I wrote to handle both the first joystick and the second joystick. Yes, that's true. You are absolutely right on Blackie. We do not want debounce hardware on the 128 joysticks because of this exact problem. So little story corner here, actually. When I was working for Coral inside of Google, we needed a way to test the big button that was on one of our products. I believe it was the AIY voice kit. Actually, this is prior to Coral. This is for AIY. And to test this, you have to physically actuate the button. And so I used an Arduino and had to write this massive debounce routine to make sure that it didn't accidentally go through all the cycles too quick. And so, yes, I hear your pain, Jens. That is exactly the same kind of pain that I had to deal with for a couple of months. Okay, so back to the code. Handle input handles both joysticks. We use X as the index into whether or not we're dealing with joystick 1 or joystick 2. Now, this is only for standard hardware. This will not work for joystick expanders. I'm not going to get into that world. It gets very crazy very fast. So handle input uses the X value as the index. And so the first thing that we do in it is we transfer X into A. This makes a copy of X and A. We then transfer A into Y. So now we've got the same value in all three registers. And then we do an address shift left. And this multiplies A by 2. So now if A had 0, it's still 0. If A had 1, it's now 2. And so we use that and then store that in X so that we can now have 2 index registers. And the way this works is we use X as the offset into our XY coordinate pairs in the sprite address location, sprite positioning memory block. We then use Y as the player number offset. So we can track the player's score using Y. We can track the player's sprite position using X. So the first thing we do is we set the interrupt flag. Now, why are we setting the interrupt flag here? Because we're touching registers. We're actually going in there and we're forcing joystick outputs on. We're telling the VIC2 that we want its outputs on. And the reason for this particular code is one of the 2 joystick ports is shared with the keyboard. It uses exactly the same inputs on the VIC2 and the CIA. All those lines are actually tied together. And if we look at the the hardware design schematic, I don't know if we can see it. Give me a split second and I'll pull it up. Yes, okay. It's going to be rotated. Unfortunately, I can't get this to change direction. But if we switch over to the web browser, you'll see that the C128 extended keyboard, this is all upside down, my apologies, is connected to the VIC. Now, if we go and look at the CIAs here, you'll see that the keyboard goes into CIA number 1, and the joystick goes into CIA number 1. And what you're not really seeing here is specifically how they're connected. But the GPIOs, or the data lines coming from the keyboard or the joysticks, are shared. So you have to think electrically here. If these 2 are shared, you have to do a trick to actually read the joystick state out of the CIA. And to do that, we force the CIA to turn its outputs on. And we do the same thing with the VIC keyboard. I'm not entirely sure why we're doing this with the VIC keyboard. This is actually a technique that I pulled out of mapping the Commodore 128. So offhand, I need to double check this one. But effectively, when we turn those outputs on, we then have the ability to read that joystick. Now, if we switch over to Vice... dang it, I didn't save. Okay, I'm not going to go through the rigmarole again. My arrow keys are actually mapped to one of the two joysticks. So if we go to joystick settings, you'll see I've got key set 1 is set to port 2. Port 2 does not have this restriction. However, if I switch this one over to joystick port 1 to key set 1, and then I start moving, you'll see all I'm doing is hitting the left arrow key, and this is implicitly hitting the enter key. Now, if I hit the right key, it moves the arrow, it does an arrow left. Down does other random things, and this is specifically because this joystick port is sitting on the same pins as the keyboard. So in the software, I mean, obviously the basic editor is not doing anything for us to try and solve this problem. They're just reading straight from the keyboard. So the end result is that if we want to read from port 1, we have to do this trick where we set these outputs on. And since we're messing with those outputs, we don't want an interrupt to occur in the middle of this, because if something else changes this output, and then we end up trying to read from the register down below here in joystick 2, then our values are just garbage, right? Yes, the keyboard is read with a matrix scan, and sometimes that does mess up the joystick matrix. There's a lot more detail on this in mapping the Commodore 128. I believe there's also some documentation inside of the Commodore 128 Programmer's Reference Guide. Offhand, I don't have all the details here. But yeah, it's kind of tricky, right? I can kind of understand why Bill Hurd continued with this design. I mean, you have to think about from the perspective that the Commodore 128 is supposed to be able to work like a Commodore 64. But if you think about the Commodore 64's hardware design, they're trying to go for bottom dollar. They had all of these things that they were going for, and like they were competing with, and they had to deal with the cheapest possible way of getting this out. So like the clean way to do this would be to add CIA number 3, specifically for another joystick. But that costs extra money, right? Your BOM cost is going to kill you. Like you end up increasing the cost of the whole unit. So when they made the Commodore 64, they only stayed with 2 CIAs. And also there's other problems with that as well, right? Like you only have a finite number of pins and inputs and all that kind of stuff. So only using 2 CIAs means they had to share these bits. And so the end result is that we have to deal with this in software, which is a lot cheaper than having to deal with it in hardware, despite the fact that the hardware is the easier solution. But in any case, we set the interrupt flag, we set the outputs on, and then we can read from this. And then once we're done with that, yes, shift registers are way, way easier to deal with. The thing is, that's still adding more chips to your BOM cost. So if you're going for bottom dollar, you don't do debounce, you don't do shift registers, you don't do any of the fancy tricks that like the NES did. You do it bottom dollar. You raw connect those pins to your CIA chip. And incidentally, they didn't even put ESD diodes there. So whenever you're plugging things in, you got to be careful because you might actually shock it. But yeah, we do this inside of an interrupt protected area because, again, we don't want to mess with these registers. We don't want something else messing with it. And so we put this in SEI CLI block so that we have an atomic read. Once we've got the joystick value, we know that we have up, down, left, right, and fire. So there's really only 5 bits that we care about. So we do 3 ASLs. So just shift all that out of the way. All the stuff we don't care about. And then we just start doing the trick that I've mentioned in the previous video. We shift each bit into the carry bit. And then if carry is clear, in other words, if that pin is shorted to ground, then we know that button's pressed. So we check fire for the first bit. The next one is we check right, then left, down, and then up. And you'll note that each of these labels is prefixed with a dot. The dot is kind of an Acme nomenclature thing. It means that this label can be reused later. You can consider this to be a local label. And effectively, each one of these routines is basically the same, but slightly different because we're dealing with different values, right? So the first one is that for checking left, we decrement the shadow sprite position. So we're decrementing the X position by 1. And we're using X as our offset into that RAM. So this is an indirect addressing mode. And then we load the tank left direction, like the sprite, tank left, which if we take a look at sprites, looks a bit like this. Right, so here's tank left, and here's all our sprites. And we divide it by 64 because the actual address here is truncated by 4, 8, 16, 32, 64, by 7 bits, right? Because the VIC is not using a full address. It's using an address concatenated with a bank location. So we divide by 64, which is just shorthand for truncating a bunch of those bits. And then we store that into the sprite pointer start address, which is not the real one. This is actually a shadow that we're messing with. So if we look for sprite pointer start in our code, you'll see it's actually at location 07F8. That is not the VIX register. That is actually our shadow stuff, I think. Hang on a minute. This may be wrong. Let's double check. We're going to double check this one. We're going to go over to the mapping doc and switch over to the webcam, or not webcam, the web browser. And I don't know why this is rotated. This is really bizarre. Page width, actual size, what the heck? Did I discover a magical thing? I think I did. Wow. What the heck? Everything's in landscape. Oh no. Okay, well, let's try this again. We'll close this and then reopen it. There we go. Right, so I don't have bookmarks in this particular PDF, and also it is also slightly OCR'd, so parts of it are good, parts of it are kind of weird, like you'll see like this is an O instead of a 0. So we have to be mindful of that. But if we look for 07F8, it's going to be way up at the top. 084, 090. Okay, it doesn't look like they actually cover that here. Oh, we're too low. That's the problem. Okay, so 866, 07 we're looking for. 08. Okay, now we're closer. 07FF. So the address we were looking for is 07F8, and then 07F8 is sprite 0. So this is not the shadow register, this is the actual register. And this is actually a little bit bad form, because we're changing the actual register for the VIC, for this particular sprite. And when we do this, this means that if the beam is in the middle of the sprite, then we're actually going to end up like with that cutoff stuff. So it's probably bad form to do it that way, but this is what I did, and we're relatively safe on this one because we're only doing this at the very beginning of the frame, so the chances of this happening are fairly low. Let's see. Yes, which sprite to use for memory for 0? Won't the shadow register potentially overwrite? I'm not sure I follow you, Greg. Can you restate? Maybe it was already answered. If you type, then I'll go ahead and see it, and I'll be looking for it. But nonetheless, we set the direction, the sprite shape, and then we load the direction, a constant, in fact, direction left, and then we store that into the sprite facing array. And this is so we know which direction that particular sprite is moving, right? So, yeah. Now, in theory, we could actually, for the players at least, we could actually use this value from the sprite shape pointer, because we know from this that we are using tank left. But for simplicity's sake, it's easier just to use a separate value for this. And then for up, we do basically the same thing, right, down. Now the fun thing here is fire. Now, we're actually, yeah, no diagonal movement in this particular game. I didn't actually code this in. The idea was to keep this as simple as possible, so I tried to keep it as simple as I could. Right, so fire actually is special, and we'll cover that in the next step. But effectively, if we run this game, you'll see, actually, I think it's just make run. Oh, forgetting this. Make test, that's right. Okay, so here it goes. We start our game. Okay, so we can move the players. Now, if I were to, do I have enough cable on this? I do. So, in my keyboard, my arrow keys are right here in these 4 buttons. Yes, no moving and fire at the same time. Not for this one. That adds a little bit, that's actually a design intention. And actually this particular joystick routine has an interesting effect to it. You'll see that if I hold down left, I can push right. If I hold down up, I can push down, down. And that has to do with how we're reading all those bits. That everything has a priority, right? Ah, yes. So, Greg, you are absolutely correct. So the kernel interrupt could possibly overwrite our sprite register. You are absolutely right. Now, if we go back to the source code, I can tell you why that actually doesn't matter. And that's because inside of our interrupt routine, the first thing we do is we disable all the basic IRQs. So this will stop all of the shadow registers in page 0, or wherever they are in RAM, from overwriting anything. So we don't have to worry about that in this case. So that's why it's not too bad. But yes, fire has the highest priority. So the tank will stop moving if I hit the fire button. If I'm holding down space, that's my fire button, and I'm pressing the other directions, nothing's happening. So yes. Oh, no worries, Greg. That's actually a really good question. So yeah, that's how this particular routine works. So, now that we've covered how to integrate joysticks into this thing, we've got our routine and all that stuff sorted out. The next step is bullets. And I'm doing this as a separate step because this is really, really crazy. We have this allocation that we have to deal with. Remember, we have 3 sprites for each player, and not all of those sprites are active at once. We may only have 1 running at a time. So, we track players and bullets in this struct of arrays. Like, essentially, you can think of it as basically an array of XY coordinate pairs, their facing addresses, and then the sprite numbers, right? In our design, sprite numbers 0 and 1 are only used for the players. This is why we can use the X and Y registers the way we do, and then use ASL to multiply those values so that we can actually get into this array and deal with player 1 and player 2. Sprites 2 through 7 are only for bullets. So, how do our bullets work? How do we want them to work, right? Bullets are semi-autonomous, right? They're not responding to input from the player. They get fired, they show up on the screen, and then they move across the screen in the direction that they were fired until they either hit a player or until they hit the edge of the playfield. Spawning will work by walking the array, the direction array, looking for the first 0. When that finds a 0, then it will then spawn a bullet at that location and then fire it off. Collisions we will handle in the next section, because that's actually another thing that we need to get into. Also, by the way, the collision routine inside of tanks is not the best option. It has problems. Part of those problems are actually caused by the VIC hardware. In this system, in this particular program, we're actually using the VIC's collision registers, which is not the best way to do this. But it was the simplest, so that's why I chose it. So bullet spawning, we're going to get into the source code. So get status, obviously I've got stuff in here, so I gotta do stash. Take a look next branch. Tech talk, step 4. Okay, and now we look at tanks. Revert, yes, go ahead and do it. So the code hasn't changed that much. We've got our init sprites, we've got all our stuff here, we've got our interrupt routine, we've got our game loop. Now our game loop has changed. We do our handle input, then we have these other functions as well. And actually I missed a function on here as well called fix up positions, which I'll get to next. Get to in a moment. But the first thing we do is we have our handle input. Once we've got our inputs sorted, we then update our bullets, we fix our tank positions, we handle our timers, and then we mark dead sprites. So let's take a look at our handle input routine, because it's where we were before. Right, so our handle input routine, again, it hasn't changed that much. The only part that's changed, really, is check fire. And if we go down to check fire, you can see the first thing we do is we load in this thing from RAM called our shoot delay counter. Remember how we were talking about that 30 frame delay? This is our counter. So we load that using Y, and Y is our player number, right? So we're basically, we have a 2-byte array that we're using here, and the first byte is for player 0 or player 1, and then the second byte is for player 2. So we load that, and then we compare it against 0. And if it's not 0, then we jump to plus, and then plus is down here, it just does an RTS. Otherwise, we load in the shooting delay. This is a constant value, which is why it's an immediate load. This is our 30 value. And then also we store that at the location. And then we call maybe spawn bullet. Now the reason I called it maybe is because we don't know at this time whether or not we have 3 bullets in flight. If we have 3 bullets in flight, we can't spawn another bullet. We're out of sprites. So this is why we call it maybe. And here's our actual routine. So X and Y contain 2 things. The first one is we have Y contains the player number. At the time this is called, X is actually containing that strided value, right? So it's actually going to be 0 or 2. So the first thing we have to do, and this is just a short bit of pseudocode so that we can better understand how we're going to do this algorithm. And that is, we need to find a free spot in the facing array. If it's 0, then set the sprite shape pointer, copy the facing from the player's orientation, and then copy the sprite position from the player's orientation. Because when we fire a bullet, we want it to start from the cannon position on the sprite. And I'm kind of sort of doing a horrible thing here. I'm actually using the exact position of the player. But there's a trick to this, because this would cause a collision, and it would actually cause your own bullet to kill yourself. So there's a trick to this. Otherwise, if we don't have a single spot in here, then we just return. There's nothing for us to do. We can't spawn another bullet. So the first thing we do is we load X with 2. And then we load the sprite facing direction into A, using X as an indexing thing. So I believe maybe I may have misexplained in the sheet for this. Yes, I did. Okay, so this design is slightly different than what the presentation talks about. We're actually using all 6 sprites for both players, because it is possible for a player to fire 6 bullets on the screen at once. Or rather, it is possible for a player not possible for a player to fire all 6 bullets at once, because the amount of time that we have in the delay between the point at which we start firing, where we spawn the bullet, and the delay between the next bullet, where the player can fire again, is enough time to only have about three bullets on the screen at once before it hits the edge, and then we can clean that bullet and then use it for the next fire. So effectively, the screen size and the speed of the bullet reduce the number of bullets on screen, so we don't have to allocate things statically using 3 bullets at once. Instead, we can actually use the entire 6 at the end. Now, I believe this may actually be causing a problem later on it, but we'll get to that later. So essentially, we just start from sprite number 2. And we load in the facing direction, because remember, the direction the sprite is facing, if it's 0, we know it's dead, right? So if it's dead, then we found a free spot. Otherwise, we increment, we go up to 8, and we keep doing this loop until we find a free slot. If we haven't, give up. Like, there's nothing we can do. So find free slot. X contains our free slot number at this point. So we set the sprite shape. We pull in the bullet. So if we look at sprites, and then we look for bullet, it just looks like a little tiny plus. Now, you may notice something funny. This plus is really, really tiny. Now, the actual dimensions of the sprite is much bigger, like you see in this giant rectangle here. But because we're using the VIX sprite hardware, it's only going to test the pixel interference between the 2 sprites. So even though the actual boundaries of the sprite might overlap with the tank just by a few pixels, it's not going to cause a collision. But we put it in the center because that's just what I decided to do. It's actually related to the shape of these tanks as well, because the tanks are centered as well. So our locations will match up. So we then copy the facing direction from the player that is spawning this bullet. Because if the tank is facing left, we want the bullet to continue left. We don't want it to go backwards, right? So we copy the facing direction and we store it in the bullet. And then we multiply the slot number and the player number by 2 so that we can find the position in the striding array. And we're doing it here because we clobbered X. Yes, it does disregard it. It has other problems though. So this is why most modern games do not use this collision stuff, because it has problems. But in this case, we transfer Y to A. We do a arithmetic shift left, so we multiply by 2. And then we transfer A to Y. Then we do the same thing with X. So transfer X to A, multiply by 2, blah, blah. They are per pixel test. It is tricky. The VIC hardware has a bug. Right, and then we copy the position of the bullet from the player. So effectively, we're using the position of the tank somewhere on screen, and then putting the bullet right on top of that tank. And then we return. So at this point, we now have an active bullet on top of the player. If we leave it there, we're going to end up with a VIC collision. We're going to end up with a collision problem. And the thing is, we're not writing to the actual sprite locations. We're writing to our shadow locations. These are not the system's shadow locations, by the way. These are ours. They're different. So we're doing a little extra work here, and that's on purpose. But effectively, we're just copying these things. And then at the end of this, we then jump back up to our check fire routine, which returns back to the sender, as I like to think of it. Return from subroutine. Or to subroutine. The moniker is kind of funny. Effectively, it just pops the location off of the stack and then jumps back to where we jumped. So, at the sound of the gong, it will be too late. The game loop. We start here. Return from subroutine. Yes, thank you, Mark. It always bugs me. Personally, like, RTS does not sound like return from subroutine because I don't think about the T in the middle of the word. So I just think return to sender because something sent me to this location, so I'm just returning back to where it sent me, which is right here. So we're We're right at this point. And so the next thing we do is we call Uptake Bullets. Now, we're doing this immediately after we've spawned a bullet. So this gives us a chance to move that bullet before we actually copy that into before we copy that position into the actual sprite registers for the VIC. And again, this is not 100% foolproof because remember, the location is copied directly from the position of the tank, and the tanks are not perfectly centered. So when we move that bullet on this update, it may not be far enough to skip that collision. But at this point in time, we haven't updated the sprite positions. So we take a look at Update Bullets. And Update Bullets, this is the routine that actually makes the bullets walk forward. So the first thing we do is we start from Sprite 2, because that's where the beginning of all of our yes, me too, Thomas, me too. But we start from from 2 because that's where all bullets are. And then we transfer X to A, so now A has the same value. We multiply it by 2, and then we transfer that to Y. So we're doing the same trick that we did before. X contains the facing offset, and all the facings are linear, and then Y contains the position offset, which is X, Y, X, Y, X, Y, right? So it's multiplied by 2. So first thing we do, increment X by 1, and we increment Y by 2, because we're dealing with a strided array that has 2 values per thing. And since we can't easily multiply by 2, we just do an NY twice. There may be a more efficient way, but if we check the 6502 opcode list, let's see, ASL takes, with the accumulator only, takes 2 cycles. Whereas doing the NY trick, where's NY? NY also takes 2 cycles, but there's a trick here. To do ASL, you have to transfer Y into A. So we're taking extra cycles by using ASL to do a multiply. So it is actually faster for us to use NY twice than do the transfer to A, do our ASL, then transfer to Y, because the transfers take an additional cycle. 2 cycles, that's right. Again, going back to the web browser, because I don't know the ISA by heart. Let's see, where is it? We want TAX, which is, or sorry, TAY, right? Takes 2 cycles. And if you really want to get into the details on that, there are 2, like you have to think in terms of what the CPU is doing, because the first thing it has to do is it has to fetch that opcode. And that's 1 cycle, straight up. Then the second cycle is, okay, I got to do that register transfer. That's your second cycle. So an NY is fetch the NY and then increment. So there's your 2 cycles. So in any case, back to the code, we compare X with 8 because at this point we're inside of a loop and we want to stop when we hit 8. Yeah, there is no in A. Can ink do A, or am I completely misremembering? No, ink cannot do A. Yeah, so if we wanted to do that, that's not actually something we can do. Really? I'm surprised to hear that the 65CO2 can. That's actually kind of interesting. Unfortunately, we're not dealing with 65CO2, so we got to do with what we got. So if we've hit 8, we're at the end of the array, we then return. Otherwise, we load the sprite facing direction from the array. And if it is 0, then we then skip any of these sprites that are marked as direction 0, which is basically just telling us it's dead. There's no point in even trying to update it. Otherwise, we take the facing direction and we logical shift right. So we're taking the bit out of that direction and we're sticking that into the carry bit. Because if we go and look at our directions, our direction flags are just a set of bits. So, and they're on the right-hand side of this 8, is it an 8? Yeah, 8-bit value. So if we shift right, into the carry register, that's actually faster than having to shift all the way left. Whoa. And I've lost my position. Dang it. Update sprite positions, that's not it. Fix up positions, maybe trigger frame. Update bullets, that's right. Right, so this is basically doing the same job as what the joystick routine does. We do the logical shifts, and then we do the carry set check, and then we update our positions, right? So effectively, we are loading in the shadow sprite position for the bullet. We're clearing the carry bit because we're about to do some addition. And when you're adding things, you always clear the carry bit. There are specific other reasons why you should do it, or not do it. But in general, when you add two values, you want to clear the carry bit. And then we add the bullet speed. So depending on which direction we're going, we're also negating this value. This is a constant value, which is why here, since if you're moving up on the bullet, you want to decrease your position, your Y position. So we use the negative version of the bullet speed. And I believe that's like 5 or something like that. Let's double check. It's 4. So we're moving 4 pixels at a time. Or, not pixels. We're moving 4 raster lines up. Because positions for sprites are measured in terms of raster lines and pixel clocks, not like pixel locations like you would have on other machines. You can kind of conflate it though, because we're doing this coordinate transform. For us, this actually is a pixel location. And then we jump next. And for the rest of them, we basically do exactly the same thing. It's all the same kind of code. We could have probably macroized this a little bit, but it made more sense to do it this particular way. And then once we're done with that particular manipulation, we then jump back up to next. So we're back at the top, and then we can finish moving the rest of the array. So back in our game loop. All right, we've just handled update bullets. So now we have to fix up our positions. Fix up positions is where we do our sprite shadow register copy. So if we go to fix up, and I meant to cover this last time, and I should have, but I did not. First thing we do is we clobber X and Y with 0, because we're starting with a clean slate. And the first thing we do is we load in the sprite position, the X value, and we compare that with the X coordinate. And basically, if X coordinate is greater than our max coordinate, then we go to check Y. And check Y, wait a minute. No. Sorry, I got this backwards. If it is less than our max X coordinate, then we set our direction to 0 because we've been stopped. This effectively marks a bullet as being dead. In the case of a player, this stops us from moving. Because I believe we were also using that as a way to increment the player's location for the player sprites. And then we set the sprite facing there. We're also pushing A because we're using A elsewhere inside of this routine. Because when we've done this check, we want to make sure that we have that value that we can then use later. And we don't want to do another load. It might be pointless to do that. It might actually be cheaper just to go ahead and load it. But because we're using an absolute address here, and we're doing indexed here, if we take a look at the opcodes again, so we do an LDA, we're actually doing an LDA absolute X. This is taking 4 cycles of time. And actually can take more if our page boundary is crossed down here. So that's a thing we have to think about. Doing a PHA-PLA combination instead, we only take, okay, this takes 3 cycles to push and then 4 to pull. So I'm actually not saving anything here. It would actually be better for me just to be loading from that location every time instead of trying to save the register. I did not look at that when I was writing this originally. But effectively, we're going to then check to see if we've hit 2 cycles. For PHA-PLA, PHA is 3. See? Yeah, and then if we take a look at PLA, PLA is actually 4. So it's really, really tricky. PHA, PLA are not really things you want to use all the time. It's not like it's not really like the way a modern RISC processor would be, like where you have a single cycle execution on every single instruction, like say RISC-V or ARM. The 6502 does a lot of cycles for everything. So unfortunately for us, that means we have to kind of sort of, if we're looking for performance, we have to really do a lot of research on this. And that's actually why I put this opcode list together. And again, this is up on GitHub, so you don't have to necessarily use the one that I've got here on nibblesandbytes.net. You can actually use whatever you like, because again, GitHub, JTGANs 6502 ops. And it's right here. It's all a single HTML file, so you can use it if you like. Yes, no pipelining. And actually, that makes things simpler for us. So we don't have to worry about cache lines. We don't have to worry about the pipeline stalls or anything like that. But in any case, once we've gotten this sprite-facing direction, recycles on all instructions. I'm not sure what you mean, Ascania. But nonetheless, our midpoint, what am I doing here? We compare to the midpoint of the out-of-bounds space. Right, so this would be the max x coordinate minus 256, or rather the negative here, and then we right shift by 1, which divides it by 2, and then we add the max x coordinate. Not sure why I'm doing that. Oh, right. I don't know why we're doing that. Let's check the presentation, because this may relate to the coordinate space. Yes, so we're going from 0 to 169 as our x coordinate. So when we do this, we're actually looking at the maximum value that we can do in a register, which is 256. We're subtracting the distance. Okay, I think I've got it in my head now. So we're taking this value here, 169. We're subtracting 256 from, we're subtracting 169 from 256. So the value from 169 to 256 is out of bounds for us. And we're looking for the middle point of that, because if we go all the way out to 256, we're actually wrapping around on the side because of the positioning of the sprites in the VIC. So we essentially take that space, we then divide it by 2 by doing the right shift by 1, and then we add the max x coordinate onto that so we can get that midpoint, right? And whichever one of those values is closer, so like the left-hand side or the right-hand side, we want to compare. And so we do this BCC, BCS thing to set the max x or the min x. Effectively, this stops the sprite from going out of bounds and either pins it on the left side or pins it on the right side. So we don't actually end up moving the sprites outside of this visible area. And then we store the X location back into the shadow sprite. We do something very similar for the Y location, although Y may actually be a little bit superfluous because, again, looking at our playfield back in the web browser, you can see we're going from 0 to 199. In this particular case, we're subtracting 199 from 256. There's really not a whole lot there. It's still good for completeness. So we do effectively the same job, right? So we're doing exactly that same thing with Y. And then once we're done with that, we then increment X, increment Y. We compare X with F because that is the end of our array. And then what in the world am I doing here? What is next doing? Fix up positions, max X. Do I even go to next? Yes, I do go to next. Right. Okay, so if we're not at the X coordinate maximum, then we just skip down to here. This is effectively our increment for the 2 offsets in RAM. So we're incrementing X and then Y. And then I don't know why we're comparing against X with F. This may be the source of one of our bugs. Yes, set max x could totally be removed. I think I went through this function like at least 100 times, changing it. So some of this may be just edits. A lot of this can probably be cleaned up. Exercise for the user. So compare x with f, and then if we're negative, then we check x. Again, I'm not entirely sure why this is happening here. I'd have to double check in some of my history. But effectively, at the end of it, we then jump back to the top of our game loop. Well, not the top of the game loop, but we jump back to where we were called, which is up here in the game loop, which I'm just going to search for because it's faster. Yeah, so at this point, just a moment. That's better. We are here. We now have to handle our timers, because when we have this bullet spawning, we don't want it to happen too fast. So we use those counters, right? And our update bullets, or rather our maybe spawn bullet thing, clears these counters and compares against these counters. But if we don't update those counters, then you'll never be able to spawn a bullet. So we check with handle timers. Handle timers, we just load in the shoot delay counter. And then if it's 0, then we just jump to the next player. Otherwise, we decrement it by 1. And if it's starting at 0, then it jumps up to FF. Next player does exactly the same thing. Probably could have done this in a more generic way. And then returns. So effectively, this is the thing that decrements our counter from 256 down to, or from 30 to 0. Sorry, I forgot we're not setting it to 0, we are setting it to 30 because we were doing a constant set. So that handles our timer counters. And then the last thing we have to do is mark dead sprites. So mark dead sprites basically is just making sure that any bullets that are off screen are deallocated. They're not active, they're not showing or anything like that. So effectively we load A with 0, we load X with 2, we then load the sprite facing value using X into A. So the load A here is actually kind of superfluous. And then we jump to our, if we're sitting at 0, in other words we're already dead, then we just go to next. Otherwise, the sprite facing value, right, the direction value will be set to 0 when it's dead. This routine goes and sets the sprites to an empty blank sprite. That's right. That's right. I'd forgotten about that. Yeah, so effectively for the code, the sprite is already dead. If we didn't have this routine, then you would have bullets that would just stay at their location visible, but we want to make them invisible. So this routine just goes in there and then sets the sprite value, the sprite shape pointer, to blank, so that you don't see it anymore. And, by the way, when we do that, that removes all the pixels. So the VIC hardware will not generate a hardware collision for the sprites if a tank is on top of a dead bullet. Well, we're not actually disabling the sprite, Mark. We're actually just setting the sprite pointer. So you see here, we load in the blank pointer here, and then we set the sprite pointer to the blank pointer. So we're not disabling the sprite. The sprites are always on. We're just changing its shape to a blank sprite. And then we walk through the rest of the list of the directions, and then if we hit 8, then we stop. So that's basically it. Like the whole routine here is basically tracking all of this extra data and then updating it in the real registers every frame. So if we actually go and run this thing with make test, and we load our game and we do our fancy fade out, and here's our game, we can move our tanks and our tanks can fire. Now you can see we've got a bug. I'm not entirely sure why that particular bug is happening. But that's the fun of this. Now, you may notice, it's kind of hard to see, but the bullet is actually spawning on top of the tank's cannon, right here. Now, in theory, this would actually kill player 1 because this actually shows up there. And so the end result is that because we aren't doing any, we have the same problem. Because we have the same, wow, that is so weird. What the heck? But because we have the bullets showing on top of each other, the bullets spawning on top of the sprite, if we leave this alone the way it is, then when you shoot down as player 1, you will be killing yourself unless we do something to check against that. But we're not checking in the bullet data to see whose bullet is whose. So in theory, it's still possible to kill yourself. And I think that's actually a bug that's still present in the game. So that's, I'll leave that up to you guys to try and fix. It's kind of a weird problem. So going back to the source, at this point, we are now in step 5, and we want to start talking about sprite collisions. Despite the fact that we have, random tanks running across the screen like crazy. And maybe we'll do that for the next live stream, actually. We can see about trying to debug that. But for now, we're just going to get into doing collisions. And so you'll see how this particular bug shows up as kind of a bigger problem. So we'll do a git stash because we've got these changes in there for the live stream. Tech Talk step 5. Okay, and then git stash pop. Okay, and now let's go back to tanks.a. Tanks.a, if I can type and spell. Jeez. Right, so everything in this is pretty much the same. We've got all our stuff in here. It all works exactly the same way. We're handling inputs. We've, yeah, it looks like the sprites, or rather the spider that flies across in Centipede. Yeah, so the big thing here at the start of the frame is we check for collisions. This is a brand new thing that we're doing. And the way collisions work, and this is a real short thing, collisions are handled with this VIC2's collision hardware. So it can tell us with pixel-perfect precision, in theory, where 2 or more sprites have overlapped or collided. So we can, it does this by way of an interrupt. And that's kind of an interesting trick. So when a collision occurs, the VIC2 will immediately interrupt the 8502. There I go again, confusing all these things. But it's causing an interrupt. So that means that we have to store that value into a shadow register somewhere, shadow value somewhere. And each frame will check that shadow location. And if a collision between a player and a bullet, I don't care who is being collided here, by the way, as long as it's a player and a bullet, then we award a point to the other player, and then we reset. Because that means that the player who got collided is dead, right? So if we go back to our code, here's where we start doing this trick. So the first thing we need to do is we need to look at our interrupt callback, because that's where we're actually handling this particular callback, or rather handling the collision. So interrupt callback. First thing we do is we act the interrupts from the VIC2. As a side note, using sprite collisions is the only way to find out what is in real memory at 0001, because normally 0001 are internal CPU locations. That's right. So that's actually kind of an interesting trick. The locations 00 and 01 are actually what control these P outputs. These are I/O locations. These are GPIOs built onto the chip. And the way you manipulate them, because the 6510 ISA does not include an in B or out B instruction like x86 does, you have to use those 2 special locations in RAM to get those values. So the only way we can actually look at those locations in RAM is to have another peripheral look at it for us. So that's what Blackie's actually referring to here. Because normally if we just do a normal LDA for those locations, we'll actually get the values of these pins, not the values in RAM. So back to the code. Let's see. First thing we do is actually, you know what? I need to step back a bit because we need to cover a little bit more about how we install that interrupt, because our values have changed. We're not just looking for the Vic raster. We also want some additional bits because we want to know about collisions. So we wedge our interrupt routine, and actually I think we're using the default values, so that may actually have interrupts for that already enabled, in which case then we don't have to worry about it. So never mind. We'll just go to the interrupt handler. Interrupt callback, which is here. And so the first thing we do is we acknowledge the interrupts. If we don't do this, the Vic will then keep that interrupt line low. And so when we come out of our interrupt and we clear the interrupt flag, we will immediately be re-interrupted. So we always have to read from this register, otherwise the Vic2 will do horrible things to us. And then we check the reason, right? So we check to see whether or not we got a raster interrupt, and then we check to see whether or not we got a collision. And what's interesting about these two functions is we have to save A, because this register has the value of why we were interrupted, why the Vic generated that interrupt. And so the first thing we do in maybe trigger frame is we push A. And this is different from earlier because we didn't have this second check, but for each one of these checks, we push A and we pull A at the end of it. So maybe trigger frame we've covered before, so we'll skip that one. Check collision is different. So the first thing we do is we save A because that's good practice. In theory, we don't necessarily have to do this because check collision is the last check that we do in this routine, but I'm doing it for completeness sake. And then we check to see why. Why were we interrupted? And we use this bit called SP collide. Now, this is defined over in macros, and this is the third bit in that particular register. So there's two of these bits. We have SPFG collide and SPSP collide. So sprites we can detect collisions between the sprite and the background and sprite and other sprites. And in the case of sprite and background, this actually refers to which bits have been turned on in the display. So again, if we go to X128 one more time, and apologies, I still have not learned to save my settings. Each one of these characters that you see on the screen, like these bits are on, right? So if we were to do a sprite to background collision, then when the sprite runs into one of these characters and one of those pixels overlaps with a pixel that is on in those characters, then we get a sprite background, or sprite foreground? I don't know why I have foreground here, but it's a collision with the background. So yeah, going back to the code, we use SPSP because we're dealing with bullets, and bullets are sprites, and the players are sprites, and everything's a sprite in this particular game, so SPSP collide. And so we check that, and if we were not triggered because of a sprite collision, we just skip it and go to out. Otherwise, we clear the collision register. So we're loading that into A. That automatically clears it. And then we set the collision flag. And then essentially what we're doing is we're using the collision register. The collision register is 8 bits, right? It's 8 bits worth of information about which sprites collided with which sprite. So we load that in A, and then we store that into the collision flag so that we can use those values of which sprites collided at this particular frame later on in the main loop. So we pull A and then we return. So in our main game loop, if I can find it, here we go. So in our main game loop, at the start of the frame, right, we're going to look for these collisions in handle collision. So handle collision is down here, and the first thing it does is it loads in that collision flag. So the collision flag bits are in the same order as the sprites. So we go from 0 to 8. 0 to 7, excuse me. And then we shift sprite 0 into the carry bit. If the carry is clear, we skip it. Otherwise, here's where we check to see if that collision occurred with a bullet. And note that we're checking on player 1 first. So if both players get hit, unfortunately, player 1 always loses in this code. But we shift that bit over, right? And then, wait, why are we doing this? So we say check player 2, logical shift right. Right, I got this backwards. So the bits are in reverse order. So it's 0 to 7, 7 being on the left. We're shifting right to get sprite 0's collision bit out, put that into the carry bit. If it's clear, then we just go check on player 2, and then we check against the bullets. So we skip sprite 1, and then we start checking. So if we are 0, yes, we can tell if it is a tank-tank collision or a tank-bullet collision. It is also possible to check bullet-bullet. But in this case, we are skipping, like the way we're doing this check is kind of unique. So you can think of this, like if we have a collision between, well, let's say it looks like this, right? So, right? And then we're going to say this is bullet 1, and then here's player 1 and player 2 and player 1, right? So if player 1 is colliding with a bullet, we know in this case that player 1 is dead. If, on the other hand, these two are 1s, we know that player 1 and player 2 are colliding, like they're on top of each other. If a bullet and a bullet are colliding like this, then we know they've crossed. But because of the way we're walking through these bits, we can actually only check for certain things. So in this case, the first thing we do is we move sprite 0 or player 1's sprite collision check into the carry bit. And if it's clear, we don't have a collision, so we can just stop looking. We don't need to worry about player 1 anymore. And we're only looking at it from the perspective of the players, not from the perspective of the bullets. So that's why when a bullet and bullet collision occurs, or a player and player collision occurs, we don't care. But it is possible. And then we skip sprite 1, and then we're doing this BEQ. So if you think about this from the perspective of the bits, right? So we've got player 1 and 2, right? If they're both colliding, then we still have entered this routine. We know that we have a collision, something has happened. One of these bits is 0. But we're shifting to the right, so that means that these two bits get eliminated, and all we have left over here are 2 zeros. So what happens is, if we have all zeros in the A register, then our 0 bit is going to be a 1. So we just know no other collisions have occurred. So at this point, we can skip that flag, we can do a BEQ, and we know that that's just going to be 0, so we can skip checking that player. In reality, we could probably actually, if this is 0, we could actually just skip the rest of the routine entirely, because all of these bits are 0. I didn't think about it from that perspective when I wrote this, so your mileage may vary. Yeah, so at this point, we've just checked to see if a collision has occurred with one of the players. If we get to this point, then we know player 1 has been hit by a bullet. We don't know which bullet. We don't really care. We just know it's happened. So we load A into X. We then start cycling the colors for the player's tank. So effectively, we just load X with A, we increment sprite color start, and then which is player 1, right? So that's their color in the registers. And then we load Y with 20. We do a busy delay loop here because it's just easier to deal with a delay this way. At this point in the game, we've essentially paused the action. We're letting the player know your bullet has collided with player 1, and hey, player 1 just died. So we're just going to cycle. And we delay a little bit. Then we increment player 2's score, and then we reset the game. And then for player 2, it works basically the same way. We do our collision flag check. We throw away sprite 0. We check by putting sprite 1's collision bit into the carry bit. If there's been no collision, we skip it. Yes, background objects make things much, much harder. And I believe that's actually a bigger problem. Yes, in theory, that would be a collision on both tanks. In this particular code, we don't check for that. So it has to be a collision between a player and a bullet. And so we actually do that with these extra shifts. So we shift out of here, and then we do the BEQ, which checks the rest of the bullets. If any of those bullets are not set, we ignore it. If it is set, then we know the player's dead at this point, so we do another cycle. And then we reset the game. Reset game, because we're basically going through all of our data and completely resetting everything, we do an SCI, because we don't want to end up clobbering the VIC registers with a bunch of data that we don't really have a lot of need for anymore. So we set the interrupt flag, we reinitialize all our sprites at the normal default locations, which I hard-coded here. Bad, June. Don't do that. Don't use constants like this. This is bad. And then we update our sprite positions, and effectively this is just going through and placing all of the things. It's copying the shadow registers and everything over. Wait, actually that's moving the players, setting their positions and moving them slightly. Oh, that's odd. And then we delay the game start. We give it a little bit of a delay because, hey, you died. You shouldn't be able to start right away. And then we clear interrupts again. And then return. And then our return routine basically just clears the collision flag and then returns to its sender. And that's basically it. So collision is basically one function and a little bit of work in the interrupt handler. And at this point, we now have a functioning game. So let's see this in action. So if we do a make test, and our game starts up, and here we go. The game has started. Oh, I didn't cover the scores. The scores are an interesting problem. Okay, so that's the next thing I need to cover. So we're not done yet. Oh, really? Okay, my apologies. I'll fix that in a moment. But at this point, we can fire bullets. We've got a little bug in there. I don't know why that's happening. That didn't happen to me when I was first testing this. There's the bug. There's a bunch of bugs. But sometimes you can end up with the player 1 running into a collision when there actually isn't a collision. Like that. And that may actually be because of a bug in the collision detection hardware. Because in theory, that should not be occurring. The two sprites are adjacent. They are not colliding. So it could also be an ordering problem in the code. The code is not 100% foolproof. As you can see, the movement is not 100% either. Still working on some of that. But we can actually kill a player, and the player 1 is then given a little bit of score. So we know the code's working. So let's check player 2. So to do that, oh no, I hit the caps key. That's not what I wanted. We go to machine settings, and then we go to joystick settings, and then we say control port 1. Oh no, wait. Those are both joysticks. We want to swap these two. Yeah, it doesn't look like there's an easy way to do it, so I'll just use key set 1 and then key set none. So now I'm moving player 2, and I can fire, and player 2 can go up to player 1 and shoot him in the head. But wait, you say, what's wrong here? We're not initializing our values right, because player 2 now has a score of 9. So also, you notice now it's going into colon, semicolon, less than, equals. So let's get into this. This is an interesting, weird problem. So we have to be able to display the score to the player. Otherwise, what's the point of keeping score, right? So in the VIX text area, you just have a bunch of numbers. So why don't we just use one of those numbers, right? It's a screen code. We know that it's an offset into a character set, and that all of the numbers in that character set go from 0 to 9. And so we can kind of just use an index into that array of the screen codes. Yeah, if you keep shooting, you'll get back to 0, right? But you'll also get like A, B, C, D, you'll get all the graphics characters, you'll get all that crazy stuff. Because we're not treating this like a BCD number. We're treating it like just a raw number, and we're just putting that into the display. So the actual routine that does that is... gosh, I don't remember what that is. I'm gonna have to find it. One of these routines actually deals with this. Cycle bullet colors, update score, that's the one. So effectively all we're doing is we're loading in the byte value of the player's score, and then we're adding the PETSCII screen code 0 to that value, and then we store it onto the screen and then set its color. So it's kind of a cheap way of doing a display of a number. You can do this for debugging in other games and stuff, and it actually helps you a little bit because then you don't have to write this crazy complicated routine to actually display multiple numbers. This is probably not the best. Yeah, it's about 30, I think. I don't know PETSCII well enough to be able to really say. That's why I used this immediate character value. It's kind of a shorthand of being able to do that. But yeah, I mean, this could be improved. So the 6510 has this mode called BCD arithmetic. Now this allows you to be able to store a value from 0 to 9 in a single register. Even though that register will allow you to go all the way up to 256, by switching the 6510 into BCD mode, you can then have it add numbers the same way a human does on base 10, rather than dealing with a base 2 and a whole bunch of bits. So that's a horrible simplification of it, but I did not know that was the same as ASCII, by the way. But the trick with this is you can use that to do calculations of the actual string value of these numbers by checking the carry bit every time you add each value, right? So you would actually store the player's score in a series of bytes somewhere in RAM, and use BCD arithmetic to add values to that. And then when you go and display it, you can use the same trick here, just this ADC 30, or the character 0, to convert that into a screen code, which you can then strip out on the screen, like as an array. So I'm not doing that here because I chose a quick and easy way of doing things. So it's up to you guys if you want to do something more. We can cover that in the next live stream, but I think at this point, I've been talking for about, I want to say a good hour and a half now, not including the the time that I wasn't actually streaming. So at this point, I want to wrap it up. But yeah, I hope you enjoyed that stream. If you have any questions, feel free to send them along. We've got the Discord channel, which I'll have a link to in the description for the stream. Yeah, see you in the next live stream. And thanks for coming.